Welcome to the second lecture in Computing Systems 2011. In this lecture we'll be looking at computer hardware. To begin with, we're going to look inside a typical desktop PC and see the different components and pieces that make up. So here's a view inside a relatively recent PC. More recent systems will look a little different. This is actually from a computer that is about 5 or 6 years old, or perhaps actually a little older than that. First of all, we can see there's a power supply. A very important component is at the back here. There's a sort of beigey brown board which has got lots of components soldered into it and other components and pieces plugged into it. This is the motherboard. There's a CPU and fan. More modern PCs will have much bigger fans and cooling systems. The CPU generates quite a lot of heat as it operates, and so these really require quite large cooling systems to keep them from melting themselves or from frying themselves as they operate. Kind of tucked away behind the cables here, but there are some RAM memory modules, and we have some plug-in boards for graphics, sound and networking. In modern PCs, again, some of these features may typically be integrated into the motherboard, so instead of having separate cards that plug into the motherboard, these features may be built into the motherboard itself. And there's a range of hard disk and floppy disk enclosures that are accessible from the front of the computer. And at the top we have some optical disks, and in a modern computer these could be CD, DVD or Blu-ray disks. The motherboard itself is worth looking more closely at, and largely it's a range of components and lots of different connectors. Very important is the CPU socket. This is where the main processor is going to go. We can always recognise this quite easily. A square shape and lots of pins. There are lots of connections. So there's lots of holes in this socket, and the CPU itself will have lots of pins on it. The slots for the RAM here. This machine has just 2 slots. That's quite common in a lot of modern motherboards. The RAM modules that plug in here themselves may have quite large capacities. Different connectors for disk drives, and expansion slots for PCI cards, and a PCI Express card slot in this machine for the graphics card. More modern motherboards may have more PCI Express slots. And a range of connectors at the back of the motherboard, and when fitted into the case these would be accessible from outside the case, so you can plug different things into and out of the motherboard. And again, we can see this is a slightly older motherboard, because for the keyboard and mouse there are the rather dated PS2 sockets. Modern computers will tend to use just USB for keyboard and mouse nowadays. Some colour-coded audio sockets, USB sockets and different video sockets, and a few others besides. A very brief glossary of some of the common terms in case you're unfamiliar with them. CPU is the central processing unit. Random access memory is RAM. So that's in contrast to example a tape where you have to read data in sequence. The random access memory, you can read memory from anywhere at any time. You don't have to read through or go through in order to find a piece of memory you want to read or write. You can write directly to any location in memory or read from. ROM is read-only memory. The BIOS is often referred to in PCs as the basic input-output system, and this is stored on an electronically erasable programmable ROM, and this contains the very basic startup software for when the machine is first switched on, so it's able to start to load things from disk and do other operations. And a term we've been encountering a few times is bus. This is a general computer architecture term for a subsystem that transfers data between different computer components, and there's a lot of different buses that you'll find in a modern PC. So here's a very general model of a computer to begin with. We have some basic components, CPU and memory and some storage, which is basically going to be a memory for the computer when the computer is switched off, and some means of input and some means of output, and all of these connected by a system bus. So it's a very general idea of what a computer is. The CPU is obviously of great interest, and we're going to be looking later in the course inside the CPU and into its workings. We generally have this and this package. It's got lots and lots of pins on it. Within the package there will be a small silicon wafer that's the actual CPU, and we can see it here in this AMD CPU. The rest of the CPU is just packaging, wiring and a few supporting components. Lots and lots of pins to connect to the motherboard, and Intel and AMD are the main producers of the x86 compatible families of processors, and these are used in most modern PCs. So most Windows PCs will be using an x86 processor, as well as modern Macs. So that's chips like the Pentium, for example, the Pentium range. The CPUs are made from silicon wafers that are processed in very expensive fabrication plants, where they actually create wafers, and the wafers are these large discs, and you can see there's lots of squares within these discs, and these are actually going to be the individual chips. So these then get cut up to form the individual chips, and within each integrated circuit you'll see there are lots and lots and lots of connections. So this is the wiring diagram for one chip cut out of a single wafer. And you can see from the different colouring schemes, different types of wiring and different patterns of wiring, and these will correspond to different components of the CPU itself. And again, we'll be looking at that in more detail later in the course. Common in modern PCs, especially of the Windows variety, we have the central processing unit, and that's connected to a couple of other chips called the North Bridge and the South Bridge. And the North Bridge and South Bridge in turn connect to a range of different buses and connections to other devices. Many of the slower peripherals will be connected to the South Bridge via different buses that connect there, whereas RAM, the main memory of the computer, which we need very fast access to, and perhaps also the graphics system on the chip on the computer, we also need fast access to that. They'll often be connected via the North Bridge, although some processor architectures actually have the North Bridge and the CPU inside the one package, or even inside the one integrated circuit nowadays. There are a range of different bus standards that have evolved over the years to support ever higher data transfer rates. Internally, there are PCI, Peripheral Component Interconnect, PCIe, which is PCI Express, this is a faster serial version, and ATA, or serial ATA, which is mainly used for disk drives. And externally, you have something like the USB Universal Serial Bus. So a computer bus can be internal, something that's a component of the motherboard, or it can be a link to something that's also external and links to external devices, such as USB. PCI and PCI Express slots are shown here in this close-up from a motherboard. We can see that some motherboards have a range of different sockets. This motherboard has two PCI Express X16 slots. These would normally be for graphics cards, and this is presumably from a motherboard designed to support two graphics cards that may be interconnected to get a very high graphical performance. You can see that different PCI Express slots can actually be of different size, and that corresponds to how many data lanes that they have. They all have a set number of lanes for power and for some basic connectivity, and then a varying number of data lanes. And so we can see PCI Express X16, which has 16 data lanes, are the longest slots there. The PCI, the older PCI slot, which is the one at the bottom of the picture, we can see it's actually quite a different design from the other ones, and that will be a slower interface, a slower bus. Now, the original PCI used a parallel bus. To understand what this does, if we consider an 8-bit parallel bus, it might use, for example, 8 wires, and so when it sends a byte, it sends all 8 bits at the one time. And when it receives that byte, it has to receive all 8 bits at the one time and then combine those 8 bits into the one byte. But there's some complexity there, that the single byte has to be split across multiple connections, and then when it's received at the other end it has to be recombined, and there can be ever so slight timing differences just because of the different lengths of the wires connecting both ends of that parallel bus. Tiny timing differences that come in here create a skew across the different wires, and this creates problems for parallel connections. You have to wait till all the bits have arrived before you can do anything, and you have to recombine the different parallel signals into one byte before you can do anything with it. And so modern computing has found that serial buses and serial connections that send one bit at a time are able to operate at much higher speed. Now, PCI Express has multiple serial connections, which is a little bit different, but is able to operate each lane independently, so they don't have to wait for each other to catch up before they're able to process the data. And almost all modern high-speed buses are serial connections. At this point in the lecture, I asked my class what was the world's most successful CPU range. I got quite a good number of answers in, quite clearly the class felt that Intel or x86 or Intel AMD was the world's most successful CPU range. But if we're thinking in terms of the number of CPUs sold, that's not actually the case. So what is the world's most successful CPU range? Certainly in terms of unit sales, it's actually the ARM computing devices, Advanced RISC Machine. And so in the first image we can see an ARM chip that's powering a network router. In the early uses of ARM, and this is still used in these areas, but ARM processors were mainly used in embedded devices such as laser printers or routers or other devices, so mainly in areas where you might not think so much that there's a computer in there, but there would be a CPU doing stuff. But over time it became adopted increasingly for a wider range of computing devices. So some years ago it was adopted for the Nintendo Game Boy Advance, and that was an important design win, I think, for ARM and for its continued success. And since then it's been used in Nintendo DS, it's been used in ebooks, it's used a lot in mobile phones, especially smartphones, it's used in netbooks, set-top boxes, it's used in the Kindle as shown here, and is also the chip that powers the iPad. And because it's used in such a wide range of different areas, it's used in printers, it's used in routers, it's used in phones, it's used in portable tablet computers, it's used in gaming machines and ebooks, it's used in a very wide range of different areas, and that has allowed it to make quite significant numbers of sales. What's interesting about ARM is the company ARM don't actually make any of the chips themselves. What they do create are designs, and they license these designs to other companies who may then go on to actually make the actual chips. And they may add their own additional customizations to the design, or they may ask ARM to adapt the designs for them, so ARM can also sell services. Or they might add additional components and then sell that. So Nvidia, for example, have a Tegra chip for mobile computing, and it combines an ARM processor core with Nvidia graphics technology. To date, over 15 billion ARM-based chips have shipped, and estimates are that they may sell approximately 5 billion this year alone. And so we are looking at a situation that within a short period of time, it's likely that they will be selling more ARM CPUs every year than there are people. So that's quite some number of chips. One of the areas where ARM chips are often used is to create something called a system on a chip. And system on a chip is quite a recent innovation, and the idea here is that we can try and combine all the components needed for a computer, or almost all, not the keyboard and not the monitor obviously, but we put all of the integrated circuit components for a computer or other system onto a single integrated circuit. Overall, designing a system on a chip can be complex and costly, and putting all of these disparate components onto a single piece of silicon may compromise efficiency of some elements, but the drawbacks are offset because you only have to make one chip to make your complete thing, and assembly costs are going to be much lower because you have less things to combine when you're actually manufacturing, and you're going to use a lot less power for running the system than if you've got lots of different chips and components. And so here's an example of a possible system on a chip, and again we can see here we've got an ARM processor core at the centre of it. We've got a bus inside the chip itself, and we've actually got a peripheral bridge at the centre here. And we can also see we've got memory controllers, and we have RAM, and we have some flash memory, and we have a number of different input and output connections. And some connections here are specifically for working with debugging and developing software for the system on the chip itself. So we have CPU, memory, storage, input, output, all these different components of a computer connected via bus on a single chip. So inside the CPU we do have a range of different components and pieces. We have a control unit or control units, arithmetic logic units. These are going to do adding, subtracting and a number of other operations. Some internal data buses to pass data around inside the chip. input-output interfaces, and some registers and memory cache, so places to store numbers and data that we're working with. This is not just for system on a chip designs, this is basically all CPUs will have these basic components. We're going to come back, as I've said, later in the course to look in more detail inside the CPU, but for now we want to consider how do CPUs represent instructions and data. Well, fundamentally we're using zeros and ones. Typically a low voltage value, for example 0 volts to 0.4 volts, is going to be used to represent off or 0, and a high voltage value, for example somewhere in the range 2.8 to 5 volts, will represent on or 1. And we use transistors, and in the olden days valves, to act as electrical switches. And a large number of transistors can be combined into a single integrated circuit. This is where computers get really their power, is by being able to combine millions of transistors into a single integrated circuit. So transistors are our basic building blocks for creating integrated circuits. And we can actually buy these as discrete components. So in the picture there we can see a few different transistors, and each of those is a single transistor. Each has 3 pins, as you can see. And the 3 connections are base, collector and emitter. And the presence or absence of a charge at the base can be used to switch a transistor on or off. So we have an example there. So some voltage in can switch the circuit on or off in effect, and that will affect the voltage out. And that circuit is actually a very simple form of transistor inverter. And in this case, if the V in, voltage in, is on, the voltage out will be off. And you can see at the emitter we've got the low voltage, and at the collector where it says VCC, on the other side of a resistor there, that's the high voltage. So when V in is off, the circuit is broken, and so we don't have a connection from the emitter through to V out, so the voltage at V out has to be VCC. When V in is on, we do have a connection between V out and the emitter, and so the output at V out will actually be the voltage from the emitter, and the presence of the resistor there between V out and VCC is what will ensure that. This is also called a NOT gate in logic circuit terms, because the output is the inverse of the input value. The table there, where we've got a table of inputs and outputs, that's also referred to as a truth table. So a truth table is one of these tables of input and output values of binary and Boolean values. So we can use different circuits of transistors and resistors to build up a range of basic logic gates. So the inverter is a NOT gate. Other gates may take 2 or more inputs, and we're going to see those in the next lecture. Before we look at logic gates though, we're going to consider just now how do we represent numbers and instructions. We're going to use strings of zeros and ones to act as instructions and data. So a particular pattern of zeros and ones may be interpreted as an instruction for the CPU control unit to tell it what to do, or could also represent data, for example as numerical inputs and outputs for the arithmetic logic unit. There's quite a lot of different things we can represent and ways of representing things, but first of all can we think about how can we represent numbers using only zeros and ones. So before we look at binary numbers, so binary values are values based on zeros and ones, let's think about how we do things in decimal. In decimal, when we write out a number, from right to left we will have columns of thousands and hundreds and tens and units. And if we added another column on the right, that would be the 10,000s. So it can be easy to forget how this works because we're so used to working with decimal numbers we don't often think about them like this. But the number 2053 is 2 thousands, it's 0 100s, 5 10s and 3 1s. That can also be written as 3 times 10 to the power of 0. So 10 to the power of 0 is 1. Any positive integer to the power of 0 is going to give us 1. 10 to the power of 1 just means 10. 10 to the power of 2 is 10 squared, and that's 100. And 10 to the power of 3 is 10 times 10 times 10 is 1000. So if we had another column there, that would be 10 to the power of 4, and that would be 10 times 10 times 10 times 10, which would be 10,000. So this number 2053 is equal to 2 times 10 to the power of 3 plus 0 times 10 squared plus 5 times 10 plus 3 times 10 to the power of 0. 2053. In binary, from right to left, the columns are the 8s, the 4s, the 2s, and then the units. So 1101 in binary, and I've put the sort of subscript 2 at the end of that number to indicate this is a binary number. What's that equal to? Well, from right to left, the columns are 8s, 4s, 2s, and units. 2 to the power of 0 is 1, so this is the 1s column. 2 to the power of 1 is just 2 itself. So this is the 2s column. 2 to the power of 2, that's 2 squared. This is the 4s column. And 2 to the power of 3 is 2 times 2 times 2, so this is the 8s column. So we have 1 8 plus 1 4 plus 0 2s plus 1 1. So we've got 8 plus 4 plus 0 plus 1. So 1101 in binary, also known as base 2, gives us 13 in decimal, which we can also call base 10. How can we convert binary to decimal numbers? It's not too difficult. So say we have the number 11001011 in binary. We have to convert that to decimal. An easy way of doing this is to identify the columns, identify the 1s, the 2s, the 4s, the 8s, and so on for as many digits as we have. And we just carry on doubling each time. So if you notice, this simply doubles. So 1 times 2 times 2 times 2 times 2. And so we keep doubling. And so to calculate this binary value, we simply have to add up the number wherever there is a 1 in the appropriate column, which will give us 128 plus 64 plus 8 plus 2 plus 1, 203, and that's our answer. So what would the decimal of 11111111 be? For any number that we're trying to work out, it's worthwhile learning how to do this in paper and understanding what to do in paper. If you want to check your answers, we can use the calculator that features in Microsoft Windows. And we can see here that there is a view. We can choose a programmer view. So this is an easy way of converting the values. And we can choose binary. And when you choose binary, you notice that we can only enter 1s and 0s now. Can't enter anything else. So 1 1 1 1 1 1 1 1 is the number we're going to translate. And if I simply select decimal now, this will convert it to decimal. And we can see the answer is 255. So try the following on paper if you haven't already, and then use the calculator to check your answers. Can you work out what the decimal value of the following binary numbers are? Inverse problem is how to convert decimal to binary. So for example, how to convert 198 in decimal to binary. And again, we can start off by creating a table of the powers of 2. We're going to work from the left to the right. We're going to enter a 1 wherever the column value is less than or equal to our remaining value. So we've got 198 just now. 128 is less than 198, so we're going to enter a 1 in that column, and we will subtract it from 198, and that will give us a remainder of 70. And then we're going to repeat what we've just done until we reach 0. So if we take away another 64, then we will now have a remainder of 6. So 70 minus 64 is a remainder of 6. And we can now take away, we can't take away 32, we can't take away 16, we can't take away 8, we can take away 4, we'll leave a remainder of 2. And finally we can take away 2, we'll leave a remainder of 0. Any remaining columns we just fill in with zeros, and that gives us the binary value 11000110. And again, here are some more numbers for you to try out and to check that you're able to solve this. And again, you can use a calculator to check your answers. Now, I've actually mentioned already, but a single binary value, a single 0 or 1, we refer to as a bit. We refer to a group of 8 bits as a byte, and also sometimes referred to, it's not actually often used, a group of 4 bits can be referred to as a nibble. Now, a separate question is, what is the range that you can represent with a certain number of binary digits? So with 8 binary digits, we saw that a binary value that was all ones gives us a value of 255. So the largest number we could represent with 8 binary digits is 255, but the smallest number is 0. So the range is how many values can we represent. We can represent all the values from 0 to 255, so we can represent 256 different values. So there is a range of 256 values there. And there's a quick way of checking how many bits we can represent with other values. And again, we can use our calculator. I'm just going to put it to the scientific view and show you that 2 to the power of 8 is equal to 256. So the number of values we can represent with 8 bits is 256. 2 to the power of 16 gives us 65,536. So if we've got a binary integer with 16 bits, we can represent any number from 0 through to 65,535. What if there are 32 bits? Well, now the number becomes quite large. And we can put on digit grouping to kind of see how big this is. So a little bit over 4,000 million. We can also do arithmetic with binary, so we can add and subtract binary values. So at the top here we can see an example where we have some binary addition. 101 plus 11. Well, we start on the right hand column, add 1 and 1. Well, the result of adding 1 and 1 is 2, but we don't have a binary digit for 2, so we've got to put the 1 into the next column, and the result is 0. So when we add 1 and 1 in binary, the result is 1, 0. So the 1 goes into the next column and the 0 goes below. So when we add 1 and 1, we have to carry 1 to the next column and put a result of 0. Now in the next column, we've got a 1 that we're carrying in, add 1. So that gives us a 1 to carry to the next column and 0 here. And then in this column, we've got a 1 being carried in, plus this 1 gives us a 1, 0 result. So 1, 0, 1 plus 1, 1 gives us 1, 0, 0, 0. And for subtraction, it's similar. 1, 0, 1 minus 1, 1. Well, 1 minus 1 is 0. We can't subtract 1 from 0, but we can subtract 1 from 1, 0, will give us a result of 1. We can also multiply binary numbers. We're not really going to look into detail in this, but it's worth noting that to multiply a number by 2 is actually quite straightforward, because all we need to do to multiply a number by 2 is shift the values to the left. So for multiplication, when we're multiplying by 2, we can actually just move all the digits one to the left and add in a 0 at the right hand side. This is similar to how in decimal numbers, if you're multiplying values by 10, again we shift all the digits to the left and we just add a 0 at the end. So we're very used to in decimal, multiplying any number by 10, just add a 0 at the end, very simple. In binary, multiply by 2, add a 0 at the end. For division, we shift right. So we can just cross off the final digit. We're not worrying just now about how we're going to represent or work with fractions. We'll see that next week. But to divide by 2, we can just shift all the digits to the right, and whatever the rightmost digit was, whether it's 0 or 1, it just gets lost. That's actually the question for next week, is how to represent negative numbers in binary. And I have to say, I got an amazing range of replies for this in the class. Some of which were spot on and some of which were off the wall. But instead of looking at representing negative numbers, instead we just considered just now how to represent text, which is something else we want to do in computers quite a lot. And the ASCII standard is actually still widely used for text representation from the American Standard Code for Information Interchange. This standard uses 7 binary bits, giving 128 different character codes. So we've got a pattern of zeros and ones that gives us 128 different possible codes, and each of these binary codes gets assigned to a different character, a different piece of text. Many of these are the alphabet characters, but there are also some control characters, such as new line. And here's a ASCII table. And the first 3 binary digits are shown along here at the top, with the number 0 through to 7. And the next 4 binary digits are shown along here. So for example, the ASCII character represented by 011 will be in this column. 011 will be in this column. So if the binary value for the ASCII character is 0111000, then we would look in this column, 011, column 3, and then 1000 is row 8. And so column 3, row 8 is actually the digit 8. And we could do a similar operation to look up any of the alphabetic characters, some other symbols like addition and subtraction symbols and equal symbols, as well as some of these character codes, special codes for the delete key or the space key. And there's even one there for the bell, which is a very simple basic sound that has its own actual code in the ASCII chart, although it's not always used now. So some of these examples, 1000001, that converts to 65 in decimal, but when we're looking at ASCII, 100 and then 001, that's character A. And then 110001 is the lowercase letter A. And some of the other symbols are there, shown there as well. But in recent years, ASCII has increasingly been replaced with other character coding systems. Why? What's the problem with ASCII? Well, very basically, it only supports the most common Western Latin alphabet, so it doesn't support all of the symbols used in European languages, let alone the languages in Cyrillic, the Eastern European or Greek alphabets, the Arabic or Hebrew alphabets, any of the Eastern languages and alphabets. So there's a whole range of languages around the world where the letters and symbols used in the language are not represented in ASCII and can't be represented in ASCII. So some alphabets Can't even just change the symbols in the ASCII table, because some alphabets have more than 128 different characters. So we can't just use ASCII, or even by replacing the different characters. Instead, a 16-bit or a 32-bit system can support vastly extended character sets. The current dominant standard for character encoding is something called Unicode, and there are over 100,000 characters in Unicode, and it supports over 90 different alphabets. And the full Unicode standard supports text for languages that write from right to left, such as Hebrew or Arabic. And UTF-8 is a Unicode encoding that uses 1 byte for ASCII characters, so ASCII code is preserved as part of Unicode. So with UTF-8, a single character might use up to 4 bytes, but an ASCII character might just use 1 byte. Final topic for this session is to consider hexadecimal. Most computer architectures support operations in 1, 2, 4 or 8 bytes. This is 8-bit computing or 16-bit, 32-bit or in Leo now 64-bit. We really need a way to be able to write binary numbers in a convenient shorthand. So we don't want to have to write out 1010111001101001. As you can imagine, it's quite tedious and also very easy to make mistakes. We could convert all our binary digits to decimal and back, but the conversion isn't an automatic process. We can certainly do it, but it's not the most simple conversion. And so what is used instead is something called hexadecimal. And here is hexadecimal. So hexadecimal is a numbering system that has 16 different digits from 0 through to 15. And for the values above 9, we normally use the letters A, B, C, D, E or F. It doesn't matter if they're capital letters or lowercase letters. And so the hexadecimal digits run from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E or F. And this table shows you the decimal values, the binary values and the hex values. And so we can see that for the binary value 1111, well that's decimal 15, we can calculate that, check that out. That converts to the hex value F, and 1010 converts to the hex value A. So to convert between binary and hex is actually very straightforward, because we can break up any binary number into chunks of 4 bits and convert. So it becomes much more straightforward. You only ever have to convert a 4-bit number at a time. If you're converting a binary number that's got 6 bits, you take the least significant 4 bits, convert that to hex, and then add another couple of leading zeros, and then you can convert it into 2 hex values. And there's another one there left as a challenge for you. And converting the other direction, each digit of a hex number represents 4 bits. So to convert BD, we convert the B and that becomes 1011, and we convert the D, that becomes 1101. And there's another challenge where you convert the C0FA in hexadecimal. What's that in binary? There was a challenge question with this week, and can you decode the secret message and what does it mean? Giving this answer in class, I have to say, from Blackboard so far, people found it a lot easier than I think I was expecting, but I'm glad that people got this little practice anyway. So here we have some hex values. Each of these hex values represents an ASCII character, which gives us a message. And then the second part of the problem is, what does the message actually mean? What's the significance of the message? And answers will be online and given in class. And key exercise for next week is to really look at how we can represent negative numbers and fractions. So far we've only used binary values to represent positive integers, positive whole numbers, and text characters, how can we represent fractions and negative numbers as well? And so there's some reading identified for next week and some further reading as well. And here are the credits for the images this week, and I'll see you later.